Hello, everyone, and welcome to our second lecture of GPU computing. Today, we're going to start talking about data parallel programming and what that means and how we do it on GPU. So last time, I gave a brief introduction of GPU computing, why it emerged, and the history behind it. And we said um, even though Moore's law predicted that, and indeed the prediction was fulfilled, that we were getting more and more transistors, almost double the number of transistors every year, and we were able to switch those transistors faster for a while. In 2005, we had a stagnation in how much we can increase the frequency of processors, and that was because of power. It was because of the power wall, and because of that, we were no longer able to get our processors to go faster and faster just by simply scaling frequency. So if we wanted to get more performance out of our hardware, what the industry did is they went towards increasing the number of cores. So in 2005, when we hit we saw an explosion in the number of cores in processors. I'm talking about CPU processors, but we also saw the emergence of parallel processors, and most notably GPUs as a form of a massively parallel processor. We talked last time about the difference between latency-oriented design and throughput-oriented design. We said that in latency-oriented design, we design our system to minimize the time it takes to perform a single task. Whereas in throughput-oriented design, we design our system to maximize the number of tasks that it can perform per unit time, even if that means it's at the expense of the time it takes for a single task. And a car and a bus were a nice example of that. If I want to get one person from A to B as fast as possible, the car is probably the better approach. But if I want to take 20 people from A to B as fast as possible, then most likely the bus will be the better approach. And the same to between CPUs and GPUs. So a CPU is an example of a latency-oriented processor, whereas a GPU is an example of a throughput-oriented processor. And we saw how this gets reflected in how these architectures are designed. In CPUs, we have a few very powerful ALUs that can finish a single operation very quickly, whereas in GPUs, we have many small ALUs that each take longer, but we have more of them, so we can do more at the same time. Same thing with caches. We have large caches on CPUs to minimize the memory access latency, whereas on GPUs, we have smaller caches in order for us to be able to dedicate more area to other things like computation. On CPUs, we have sophisticated control, again, to minimize the latencies so that we minimize how many stalls we have because of control operations, whereas on GPUs, we have much simpler control. And also multi-threading on CPUs, because we don't have a lot of latency to hide because operations are short latency, we have only a few threads running per core, whereas on GPUs, we have many more threads per core because we have more stalls in our pipeline that we need to hide by having multiple threads. And then finally, CPUs have high clock frequency and GPUs have moderate clock frequency. We saw how after introduction 7, which enabled people to program GPUs in a general purpose, an explosion in the number of applications that used CUDA, and then in general in the number of supercomputing teraflops that GPUs were providing in supercomputers around the world. And we also have seen an explosion in the number of developers who can develop in CUDA. All of that because GPUs have been shown to be so useful at extracting performance from applications that have a lot of parallelism. And then we the down for GPUs, and we said that even though GPUs are very successful at parallelizing high performance computing applications, scientific applications, machine learning applications, that's actually only one of the market segments of GPUs, but there's all kinds of other market segments, and all of these other market segments are also important, and they have an impact on the way GPUs are architected. They have an impact on what goes in and what doesn't go in to GPUs, and they also have an impact on the fact that these GPUs the cost of manufacturing these GPUs can be amortized across a large volume of sales to make them affordable. And this is even though in the course we are going to be focusing on mostly data center applications, scientific computing applications, maybe machine learning applications, really GPUs are used for a wide range of application domains. And with that, I looked at, and I said that the first 3 weeks of the course are going to be spent talking about the fundamentals of GPU computing, at the basic programming model. We're going to look at the basic architecture of a GPU. Then the next 7 weeks we will look at different parallel patterns, so common computations that are performed in different applications and how we parallelize those computations. And then in the final 3 weeks we'll look at some advanced features of GPU programming. So this is what we covered last time. Anybody have any questions before we kind of jump into today's material? Okay, well, in that case, we're talking about data parallel programming, and in particular, we're going to introduce data parallel programming in the context of the CUDA programming model, which we will be using in this course. CUDA is one of multiple programming interfaces available out there, or CUDA is a platform. CUDA C, which we'll be using in this course, is one of the programming interfaces for programming GPUs. There are many others out there, but we'll be focusing on CUDA because of its popularity. So today we'll introduce data parallel programming using CUDA, and we'll use an example of the concepts that we will be talking about. There's approaches to you guys looking? Oh. These VP access the so they can demo and not very good.
Professor, we can't hear anything from your end.
Can you guys hear me better now?
Yes.
Yes. Now it's good.
Is this better? Okay. Okay. So the problem is that I'm connected to the university's VPN because I need to connect to a university server in order for me to demo some of the code that we're going to run in this lecture. And when I connect to VPN, now all my internet traffic goes to the university VPN, so it slows everything down. So I hope this doesn't continue. I hope what I did just now just works. Is it still lagging, or is this better?
No, it's much better.
It's working perfectly fine now.
Okay. So let's. I hope that works. My VPN disconnected. Let me make sure it reconnected. 1 second. It's reconnected. Okay, so let's hope this works. The first major kind of category of parallelism or type of parallelism is task parallelism. And the other kind of major type of parallelism is data parallelism. And these are two different approaches of extracting parallelism from applications, and you can do both of them together, okay? So task parallelism refers to when we have different operations that are performed on the same or on different data being done in parallel. And data parallelism refers to when we have the same operation being performed on different pieces of data being done in parallel, okay? So an application may have multiple tasks. Some of these tasks may be dependent on each other, or some of these tasks may be independent of each other and can run in parallel, okay? And that is an example of task parallelism. So for example, if you have, let's say, maybe you have a text editor, or you're using Microsoft Word, for example. And when you're using Microsoft Word, maybe you have your editor that is editing the text, and then you also have a spell checker that's running in the background. So the spell checker can run in parallel with your text editing, for example. And that's an example of task parallelism. You have two different tasks. These tasks do different operations, and these different operations may be done on the same data or may be done on different data, but they're different operations. So this is referred to as task parallelism. Data parallelism, on the other hand, is an example of where you have the same operation being done on a very large amount of data. And a very obvious example of this is, something like a screen, and that has pixels, and you need to compute the value of each pixel, right? So all the operations you need to do to figure out the values of all different pixels are very similar operations, but each of them is done on different input data in order to calculate different output data. And this is called data parallelism. Now, usually with task parallelism, you can only unleash a modest amount of parallelism, because usually, how many, in any application, how many different kinds of tasks do you typically do at the same time? Not that many, right? And you can imagine, for every different kind of task you have in an application, that means the programmer wrote a kind of different function or a different, set of code that is going to run. So obviously, you're not going to have thousands or millions of different kinds of tasks, each running different kinds of code available in your application. So usually, the amount of task parallelism in an application is small. On the other hand, with data parallelism, there's potentially massive amounts of parallelism that can be unleashed from a massive amount of data. And this is the type of parallelism that's most suitable for GPUs. Why? Because to increase the amount of data parallelism in a program, you don't really have to write more code to do that. It's just that you're taking the same program and running it on a much larger data set, right? If I have a screen with higher resolution, I have more pixels, and automatically I have more data parallelism. I don't really have to write new code for that. And that is why data parallelism has higher potential for releasing a massive amount of parallelism, and that's what makes data parallelism very suitable for GPUs. That's not to say that we don't run applications with high amounts of task parallelism on the GPUs. We could. It's just that data parallelism is the more natural fit for running on a GPU. Now, to show you kind of an example of data parallelism and how we can capture that on a GPU, I'm going to start with a simple kind of computation, which is vector addition. So you can think of vector addition as the hello world of data programming. Okay, what is vector addition? Well, vector addition is simply adding two vectors. So I have an input vector x and an input vector y, and I add these two vectors to get the output vector z. Okay, so how do I add x and y to get z? Well, I add the first two elements to get the first output element. I add the second element from the two vectors to get the second element. I add the third element from two vectors to get the third element, etc. Okay. Now, if I wanted to program this sequentially, how would I do it? What would I do? Well, very simply, I would just write a loop that loops through these vectors, okay, and adds each element and stores that result in the output. So we loop over the size of the vector, and we load an element of X, load an element of Y, we add them, and we store that in Z. Okay, and let's actually do that just to kind of get familiar with the code we'll be writing in class. So this happened when my VPN disconnected. Okay, so over here, I just prepared some code for us to set things up. Here, this is CUDA device synchronized. Don't worry too much about what this is doing. Over here, I have some code that allocates 3 arrays, X, Y, and Z, and that initializes X and Y to some random numbers. Okay, and then after that, what I'm doing is I am calling a function vec_add_CPU that's going to add these 2 vectors on the CPU, and I'm timing how long that takes, and then I'm going to add. I'm calling vec_add_GPU, which is going to add these 2 arrays on the GPU, and I'm timing how long that takes. Okay, and then I'm freeing X, Y, and Z. So this is what this code here is doing. And what we're going to do is we're going to implement vec_add_CPU, and then we're going to implement vec_add_GPU. Okay, so we're going to see how to do the addition on the CPU, and we're going to see how to do the addition on the GPU. Okay, so let's start with vec_add_CPU. So here, vec_add_CPU, it takes an array X, an array Y, and adds them together to produce an array Z. And N here tells me the size of the arrays. Okay, so how would I do this addition? Well, it's very simple. I'm simply going to have a loop. So I'm going to write for unsigned int I equals 0, I is less than N, plus I. Okay. So I have this this for loop that loops over the elements of the array, and then for every element of the array, I'm going to write Z of I is equal to X of I plus Y of I. Okay, easy enough. Any questions so far? Okay, great. So let's go back to our slides. So this is the code that we just wrote, and throughout the class, whenever we write code together, I'll try to have it in the slides for you guys so that you can refer to it later on. Okay, so now you know what vector addition is, and now let's go and see how we can do this vector addition in parallel. Okay, how can we take this vector addition and rather than doing it on the CPU sequentially like I just did, send it to the GPU so that it can be done on the GPU in parallel. And before we talk about that, I want to talk a little bit about how a system that has a GPU is organized. So a system, conventional system typically has a CPU, okay, and that CPU has access to some main memory. And in the context of CUDA and GPU programming, we're going to call the CPU the host. And the reason we call the CPU the host is because it's kind of like the main processor that's hosting the GPU with it. Okay, and in the main memory, we're going to call that the host memory because this is the memory that the CPU, which is the host, typically uses. Okay, and now this is a typical system. You know, we have a CPU that has access to some memory. Now, when we want to use GPU computing, we're also going to have a GPU in our system. So we're going to have a GPU, and maybe we can have multiple GPUs. But for now, we're just going to worry about having one GPU. Okay, so we're going to have a GPU, and the GPU is called the device. Okay, and the GPU has access to its own memory. Okay, this is the GPU memory, and we also call that memory sometimes global memory. And the reason we call it global memory is to distinguish it from other types of memory that the GPU has access to that we will talk about in a few lectures from now. Okay, but for now, we're just only going to worry about this one memory that the GPU has access to, which is the global memory. Okay, so the CPU and the GPU have separate memories and they cannot access each other's memories. Okay, unless you use something like unified virtual memory, which is also an advanced topic that we will talk about later in the course. But for now, we can assume that the CPU cannot access the GPU's memory and the GPU cannot access the CPU's memory. Okay, so if I allocated these arrays in memory and I want to add them, these arrays are going to be in the CPU's memory, not in the GPU's memory. So if I want to use the GPU to add these arrays, what do I need to do?
Send them through PCIe.
Right, what I need to do is I need to transfer the data from the main memory of the CPU to the memory of the GPU. And here to do this transfer, I'm going to have some kind of interconnect. And you're right, one kind of interconnect is PCIe. That's a very commonly used interconnect. Another interconnect is NVLink, which is specific to NVIDIA, but the general one is PCIe. Okay, so the main memory of the CPU is going to be connected to the main memory, the GPU memory, or the global memory of the GPU, using some kind of interconnect like PCIe. Okay. And what we need to do now is we need to transfer the data from the main memory of the CPU to the global memory of the GPU. Okay, so the typical sequence of offloading some computation from the CPU to the GPU is 1, to allocate memory on the GPU, 2, to copy the data from the main memory of the CPU to the GPU, 3, to perform the computation on the GPU, and obviously to perform the computation, the GPU is going to have to access its memory to get the data that needs to perform the computation on. And then 4, copy the data from the GPU memory back to the main memory. And then 5, deallocate memory from the GPU. Okay, so we have to allocate, copy, compute, copy back, and deallocate. Okay, so these are 5 different things that we need to do, and today we're going to look at how to do these 5 different things for the vector addition example that we are looking at. Okay, and let's start with allocating memory. So
can I ask a question, please?
Yes, go ahead.
I'm the physicist, so I have a simple question. When you say main memory for the CPU, is that just the RAM, or?
Yes, when I say main memory for the CPU, I'm referring to DRAM. You're right.
Okay, thanks.
Okay.
Yeah, thanks.
Okay. All right. So somebody's asking if this is a standard workflow. This is the typical sequence of operations you would do whenever you want to offload some work from the CPU to the GPU. This may not necessarily be the most efficient way of doing things, and we'll look at we'll look at how to make this more efficient in the future. But for now, we can just go with this workflow. Okay. All right. So CUDA memory management. How do I allocate memory on the GPU? Well, there is a function that's part of CUDA called CUDA-malloc that allows you to allocate memory on the GPU. So when I write CUDA-malloc, CUDA-malloc takes 2 arguments, a device pointer, and this is a pointer to where I want to put the pointer to the memory I allocated after I call CUDA-malloc, and then again the size of the data that I want to allocate. Okay, so let me go back to our code and see how we can use CUDA-malloc in order for us to allocate memory on the GPU. So now I want to go and I want to implement VecAddGPU, and we said that the first step of implementing VecAddGPU is to allocate the GPU memory. Okay, so how are we going to do that? We said we're going to use CUDA-malloc. So what I'm going to do is I have a pointer here. This X over here points to the data for X on the CPU memory or the host memory that was allocated using malloc. Same thing for Y. Same thing for Z. So what I want to do is I want to now allocate memory on the GPU. So I'm going to declare new pointers. Okay, and there's a convention that sometimes we follow. You don't have to follow it, but that's just a convention that some people follow, which is that I'm going to call it X_D. So here, X_D, the underscore D refers to the fact that this pointer points to the device. I don't have to write _D. I just choose to do it because it makes my code easier to read and understand. I know if I see _D, I know that this points to something on the device. So here I'm going to have X_D, another pointer Y_D, and another pointer Z_D. Okay, and these 3 pointers I'm going to use for allocating memory. So how do I do that? Well, I'm going to use CUDA-malloc. So I write CUDA-malloc. Okay, and now CUDA-malloc is going to take X_D as an argument, but we know that functions cannot modify arguments. So if I want CUDA-malloc to modify X_D, I shouldn't give it X_D. I should give it a pointer to x underscore d. So I'm going to give it a pointer to x underscore d, and I'm going to tell it how much memory I want for it to allocate. And the amount of memory I want for it to allocate is the same amount as the memory I want for x, which is n, the number of elements in x, times size of float, which is the size of each element of x. Okay, so I'm going to write CUDA-malloc size of x underscore d, size of float. And what this is going to do is it's going to allocate n times size of float bytes in the GPU memory, and then it's going to return a pointer to that memory by modifying the value of x underscore d to hold that pointer. Okay. Now I usually use the same CUDA-malloc to allocate all kinds of types. Sometimes I allocate floating point arrays. Sometimes I might allocate integer arrays. So to be able to use the same CUDA-malloc for all these different kinds of data types, the CUDA-malloc actually takes a void pointer as an argument. So whenever I pass something to CUDA-malloc, a pointer to CUDA-malloc to allocate my data, it's good to cast it to a void pointer so that your compiler, a void pointer, so that your compiler doesn't complain about the fact that you're passing a float double pointer to a function that's expecting a void double pointer. Okay. And then I'm going to use the same approach to allocate y and z. So I'm just going to use CUDA-malloc because y and z, they're all the same size and they're all the same type. So I'm going to allocate y and z in the same way. All right, any questions? Right, so somebody is asking, does it return an error? And you're absolutely right. So this return type, CUDA error t, what it does is that if there was some kind of error when I'm trying to allocate memory, then it's going to return an error. And we'll see later how we can check these errors. But for now, let's confidently assume that we're not going to have errors in CUDA-malloc because we're very good at using CUDA-malloc. Okay, but you're absolutely right. So if there's an error, it's going to return an error. And the reason why we're not doing x underscore d equals CUDA-malloc is because we want to use the return value as an error code, and that is why we are passing the pointer that we want, where we want the result to be as a parameter, as opposed to what we did down here, where we did x equals malloc something. Okay. Somebody's asked me to read what underscore d is. Here, underscore d is just a convention that I'm using to remind myself that this pointer x underscore d points to data on the device. Okay. That's all what it is. You don't have to use underscore d. You can use underscore g, or you can just call it a. You can call it anything you like. I'm just using x underscore d because it helps me remember, so that later on, if I want to, if I try to, for example, do x underscore d of 5, then I know I'm doing something. I can tell, oh, this is a function that runs on the CPU, but I'm trying to access data that should be on the GPU, so I should not be doing this kind of dereference. Okay, so just to help me remind myself, but you don't have to use that convention if you don't want to. Okay, so now we've seen how to allocate memory on the GPU. Of course, just like we allocate memory, we also need to deallocate memory, and there's a corresponding function for that called CUDA-free. So here, CUDA-free takes a pointer to the array that you want to deallocate, and it deallocates that from the GPU. And even though here we still need to copy to the GPU, and we need to run the GPU code, and we need to copy from the GPU. Okay, and then after that we're going to deallocate GPU memory. I'm actually going to write it down now, and it's good practice for you if you're a C programmer or a C++ programmer. You're probably familiar with all the problems that come up from having to do manual memory management and doing allocating and then forgetting to free. So for me, I find it a very good practice that every time I write a malloc, I write the corresponding free immediately, and similarly, every time I write a CUDA malloc, I write the corresponding CUDA free immediately, so that I don't forget to free. So the way I'm going to free, after I'm done with doing all of this, the way I'm going to free X, Y, and Z is by calling CUDA free. So I call CUDA free X underscore D, and I'm going to do the same thing for Y underscore D and Z underscore D. Okay. So now I've allocated my GPU memory. I'm going to do a whole bunch of stuff, copy, run, and copy back, and then I'm going to deallocate my GPU memory. All right. Okay, and as one of you mentioned, the return type for both CUDA-malloc and CUDA-free is indeed CUDA error T, and this is an error code. Each of these functions return an error code that help us with error checking that we will talk about later. Okay, so now that we know how to allocate and deallocate data, the next step is to copy data to the GPU and copy data back from the GPU. And the way to do that is by using a function called CUDA memcopy. So CUDA memcopy takes a destination address, a source address, the size of the data that I want to copy, and then the direction I want to copy, the direction of the copy. And that direction could be, the most common ones are host to device and device to host. That's where I want to copy from the CPU to the GPU, host to device, or from the GPU to the CPU, it's device to host. But other possible ones are host to host and device to device. So maybe I want to copy something from one place in the GPU to another place in the GPU. I can use device to device. Okay. Let's take a look at how we can use CUDA memcopy. So here, what arrays do I want to copy? So I allocated X, Y, and Z. What arrays do I want to copy from the CPU to the GPU? Do I copy all of them? Right, I just need to copy X and Y. So the way I do that is I'm going to write CUDA memcopy. Okay, the destination goes first and then the source. So what's the destination array in this case? If I want to copy X, I'm going to copy from X to X underscore D. So the destination is X underscore D. The source is X. The size is going to be the size of the array, which is this, which is n times size of float, and then the direction is going to be CUDA memcopy host to device. Okay, and then the same thing is gonna happen for Y. I'm gonna copy from Y to Y underscore D from Y. Okay, so these two calls are gonna copy data from the GPU to the CPU, sorry, from the CPU to the GPU. And then somehow I'm going to run my code on the GPU that does the addition, and we'll see how to do that later. And then I'm going to use the same CUDA memcopy function, but this time to copy back. So I write CUDA memcopy. And this time, what's going to be my destination? Well, first of all, what array do I want to copy back? The result array, which is Z. So what's my destination pointer going to be? Right, it's going to be Z. So I'm going to copy it to Z from Z underscore D. Okay, and the size is also going to be n times size of float. And the direction is going to be what this time? It's going to be device to host. Okay. Okay, great. So now I have the code to copy my data to the GPU. Sorry, to allocate my data on the GPU, copy it to the GPU, and then copy back from the GPU, and then deallocate. So now my data is on the GPU, everything's set up. Now all I need to do is somehow run this addition code on the GPU, and let's see how to do that. And by the way, this is the code that we just wrote together. Like I told you, I will try to always have the code for you guys to be able to refer to later on. Okay, so now
can I ask a question?
Yes, question?
Yes, sorry for cutting you off, but I have a question.
No.
Instead of copying X and Y from, so when you initialize X and Y initially with a random function, you initialize that in the sort of host memory, right? And then you're copying it?
Yes.
Can you initialize it in the device memory immediately?
Yes, I mean you can allocate. You don't have to allocate on the CPU. You can allocate on the GPU and go initialize on the GPU. But a lot of times the data that you copy to the GPU is data that you might have read from some file. So here I'm initializing it randomly, but sometimes you might have read this data from some file. Okay, or maybe you received this data over the network from some other computer. And you can't read from a file directly to a GPU, at least not in current GPUs. And that is why you normally wouldn't do that for the very initial data that you want to copy. But yes, if your computation is such that the actual data that you care about here is random numbers, you can definitely just allocate on the GPU and initialize the random numbers on the GPU.
Okay, thanks.
Yeah, you're welcome. Okay, so now that I've done this, now I want to go back to my vector addition, and I want to do my vector addition in parallel. I don't want to do it sequentially. We said these GPUs have all these massive number of threads that can run in parallel. So what I want to do is I want to do my vector addition in parallel. Okay, so how do you think I can parallelize this vector addition? So if I want to add these two vectors in parallel to get the output vector, what's one way to do it? What's the most obvious way to do it?
Split the vector.
Each boxes, a thread controls them.
Right, exactly. So I can just launch as many threads, as I have elements in my array, and then I can have every thread be responsible for adding one of these elements and storing the result. Okay, so I assign one GPU thread per vector element, and then the GPU thread is going to load two elements and store the output result. Okay, so now what we still need to do is we need to write a program that runs on the GPU that assigns every thread to one of these elements to do the addition. Okay. Somebody's asking, do we still need a loop for that? Well, we're going to see how to do it. Okay, so kind of hold on for a little, and we'll see how to do it. Okay, so before I talk about how to do this, I want to talk a little bit about how threads on the GPU are organized. So an array of threads on the GPU is called a grid. So when we from the CPU, when we create a whole bunch of threads on the GPU to perform some operation, these threads are organized onto grids. So we say that we launch a grid on the GPU and the grid is going to be an array of threads that are going to perform some computation. And we actually have a two-level hierarchy. So all these threads in the grid are just not going to be all completely independent from each other. The threads are actually going to be organized or grouped into thread blocks. Okay, so I have a grid, which is an array of threads, and these threads in the grid are going to be grouped into thread blocks. And there's a significance for this that we won't see today. We're going to see later on. But later on, we're going to see that there's the threads in the same block can interact with each other and collaborate with each other in ways that threads in different blocks cannot. And this is why we organize our grid into blocks. But you don't have to worry about that too much for now. I just want you to know that these threads are organized into blocks. Okay? Now, so what I would like to do is I would like to launch a grid of threads. And to launch a grid of threads, I actually need to specify how many blocks I want in my grid and how many threads I want in each block in my grid. So when I launch a grid, the threads in the same grid all execute the same function known as a kernel. Okay, the threads in a grid all execute the same function known as a kernel. And the way to launch a grid is by calling this special function, which we call a kernel, and telling this function how many, what's the grid size? In other words, the number of blocks in the grid that I want, and what is the block size? In other words, the number of threads in each block I want. Okay, and I'll show you how to do this. Let's go back to our code. So over here, when I say run the GPU code, what I actually want to do is I want to call a GPU kernel function. And by calling a GPU kernel function, what this will do is it will launch a grid of threads on the GPU. Okay, So the way to do that is, let's assume I have some kernel function that does this vector addition in parallel, and I'm going to call that vec_add kernel, and we'll see later on how we're going to implement vec_add kernel. Okay, so let's say I have a function vec_add kernel. What do I need to give this function? Well, I need to give it the where to find the data on the GPU. I'm going to give it x_d. I'm going to give it y_d, and I'm going to give it z_d. So this way, this kernel function knows where to find my data. And I'm also going to give it n because it needs to know the size of the array. Okay, so this is the data that my kernel function needs to know to execute my grid on the GPU. But what I also need to tell this kernel function is I need to tell it how many threads I would like for there to be. Okay, and that's going to have two parts of it. We said that threads are organized into blocks. So what I need to tell it is how many blocks I want, and I also need to tell it how many threads per block I want. Okay, so I'm gonna write these down. I'm gonna have const unsigned. It doesn't have to be const. I don't plan to change it later on the program, so I like to use const where it should be used. So I'm going to have the number of threads per block, okay? And this can, there's many different numbers, right? We're going to do it according to n, of course. So the number of threads per block, a typical number of threads per block is maybe 1,024 threads, 512 threads, 128 threads. That's kind of a typical range. We'll see later, the maximum number of threads per block that we can have on current GPUs is 1,024. We'll see later how to reason about what is the best number of threads per block to choose for our program. For now, I'm just going to set my number of threads per block to 512. Okay. So if I have a total of n elements in my vectors, that means I want to have n threads in total. Okay, so if I have 512 threads per block, then how many blocks do I need? The number of blocks I'm going to need is, okay, if I want n threads and I have 512 threads per block, right? I'm going to need n over 512 blocks. Okay. So n over 512 blocks times 512 threads per blocks gives me a total of n threads. Okay. Now the way that I tell my kernel to use this many blocks and this many threads per block is by using this special extension. And now here we're going to start to see the things that are not part of C but that are part of CUDA. I'm going to have these triple triangle brackets. Okay, somebody's asking about rounding. Yes, we will talk about rounding soon. But for now, we can just assume that n is a multiple of 512. So don't worry too much about rounding for now. Okay, so I'm going to have these triple triangle brackets. And in these triple triangle brackets, I need to provide what we call the configuration. The configurations are basically the number of blocks and the number of threads per block. So I'm first going to provide the number of blocks. Okay, you don't have to put a space. I'm just a little bit... I have a particular way that I like to write my code in, so I like to put a space there, but you don't have to. And then I'm going to tell it the number of blocks and then the number of threads per block. And now what this does is it's going to create it's going to create a grid on the GPU. This grid is going to have n over 512 blocks. Each block is going to have 512 threads. And each thread is going to execute this function called vec_add kernel, which we haven't defined yet, and we will define soon. Okay. So again, this is the code that we just wrote. We define number of threads per block, the number of blocks, and we call the kernel, provide the configurations, and then provide the parameters, which is the data that it. Okay. Any questions so far? Okay, so someone's asking why is number of blocks 512? Well, we said that we want a total of n threads. So if I have 512 threads in each block, then the number of blocks I need is n over 512, so that I will have n threads in total, because n over 512 times 512 is n. Okay, not exactly. Somebody pointed out rounding issues, and we will talk about them.
Doctor,
Yes.
can you repeat why threads are divided into blocks? Is it just like, why divide into pages to avoid fragmentation or something?
I did mention this very briefly. I said that the reason we organize threads in a grid into blocks is because threads in the same block are able to collaborate with each other in ways that threads in different blocks cannot. And that's not something I will elaborate further on today. We will talk about that in a lot of detail in a later lecture. Okay? But for now, all you need to know is that these threads in the block can collaborate with each other in special ways, but we won't use that feature today. Okay?
Thanks.
Okay, next, what we need to do is we need to implement this vec_add kernel. So now we're calling this vec_add kernel to launch a grid on the GPU. Now we have n threads running on the GPU. These threads are going to execute this vec_add kernel. So how do we implement a vec_add kernel? So a kernel is similar to a C or C++ function. However, it is preceded by the keyword global to indicate that this is a kernel. Okay, and it's going to use some special keywords in order to distinguish different threads from each other. Okay, so this vec_add kernel, to implement it, I'm just going to declare it like a regular C function. So I'm going to write void vec_add kernel, and I'm going to give it the same parameters I gave to my vec_add CPU function. Okay, but the key difference is that to indicate that this is a special type of function, it's a kernel, I'm going to precede the declaration with the keyword __ global __. There's two underscores here. Okay, so this keyword over here indicates that this function being declared is a kernel. You don't have to write _kernel at the end of it. You can call it anything. You can call it vec_add device. You can call it device vec_add. You can call it I don't know, ABC. You can call it whatever you want. I like to use the convention of using _kernel after the names of the kernels, but you don't have to do that. Okay, so now that we've declared this kernel, and now what we need to do is we need to write the code that each thread is going to execute, because we said that all the threads launched by this call are going to execute this kernel. Now, in order for threads to execute, what they need to do is they need to find a way to distinguish themselves from each other. So thread 0 needs to know that it's thread 0, thread 1 needs to know that it's thread 1, thread 2 needs to know that it's thread 2, so that they know what data to access. And for that, there are several keywords inside of CUDA that assist threads in doing that. Griddim.x tells a thread what is the number of blocks in our grid. And we're going to see later on that we can actually have multi-dimensional grids. Today we're just using a one-dimensional grid of threads, and that is why we're just going to use the .x. So .x is the first dimension. So griddim.x will tell us the number of blocks in the grid. Okay, in this case, that's going to be n over 512. Okay, and then we have blockindex.x. So blockindex.x tells a thread what is the index of its block with respect to other blocks in the grid. So any of these threads in this green block over here, if they call blockindex.x, then they will get the value 2. So all these threads, their blockindex.x is 0. All these threads, their blockindex.x is 1. All these threads, their blockindex.x is 2, etc. Okay. Then we have blockdim.x. So blockdim.x tells a thread how many threads there are per block. And again, blocks can be multi-dimensional, so that's why we have the .x over here. So in this case, blockdim.x would be 4. In reality here, our blockdim.x corresponds to the number of threads per block, which is 512. And then finally, we have threadindex.x. Threadindex.x tells a thread what its index is relative to other threads inside of its block. Okay, So here for this orange thread, if the orange thread reads griddim.x, the value will be 4 because we have 4 blocks in the grid. If it reads blockindex.x, the value will be 2 because the index of its block is 0, 1, 2. If it calls blockdim.x, it will get 4 because there are 4 threads in the block. And if it calls threadindex.x, it will get 1 because its index with respect to other threads in its block is 0, 1. Okay. Now, if I want to find the index of this orange thread with respect to the beginning of the grid, so in other words, its global index, then in this case, what I would do is I would take the block index, which is 2 blocks, multiply it by the block dim, which is 4. That gives me 8 threads. And then I would add threadindex.x, which is 1. So the index of this thread would be 9. Okay? And that's going to be important. Why? Well, because if we want to do parallel vector addition, then what we're going to do is we want to map each of these threads to one of these elements in the array. So each thread is going to have to compute its global index or its index from the beginning of the grid to find out the index of the element from the beginning of the array that it wants to access. Okay? So let's see how to do that. So inside of vec_add kernel, the first thing the thread needs to do is it needs to identify its global index. Okay, so we can write unsigned int I is equal to, and again, to identify the thread's global index, we're going to do the size of a block times the number of blocks plus the offset of the thread. Okay, to get to this thread. So the size of the block is blockdim.x. Okay, the number of blocks is going to be blockindex.x. So we have blockdim.x times blockindex.x. Okay, and then the number of threads from the beginning of the block, so the index of the thread with respect to the beginning of the block is going to be plus threadindex.x. Okay, and now here I is the index of the thread from the beginning of the block. Okay, somebody's asking me why it needs to be global. What I mean by global is I want the index of the thread, the keywords that are provided to me in CUDA tell me the index of the thread with respect to the beginning of the block, not the beginning of the grid. Okay, but what I want is I want the index of the thread from the beginning of the grid. That's what I mean by the global index. Okay. Okay. Somebody is asking, is the x over here the same as the x over here? No, it's not. Here, this x is a pointer to an array. Here, this x over here is a field inside of the blockdim structure. So here, blockdim is a structure. It has x, y, and z, but we're not going to worry about y and z for now. We'll worry about them next time. Okay. Okay. So somebody's asking, how is this code compiled to the GPU? I'll cover that later on in today's lecture. Okay, so don't worry about that for now. For now, I just want to make sure everybody understands how blockdim.x times blockindex.x plus threadindex.x gives me the global thread index. Okay, is that clear to everyone? Okay. So now that I have the thread's global index, so now that I know the index of this thread with respect to the beginning of the grid, now what I can do is I can use this index to perform whatever operation I perform. So now that I have this index, what do I do here? What code is the thread going to execute? Well, I'm just going to do z of I is equal to x of I plus y of I. Okay. So now every thread that gets launched by this call is going to execute the same code over here, but each one is going to have a different threadindex.x and a different blockindex.x, and therefore each one will have a different I, and each one is going to add a different set of read different x of I and y of I, and store to a different z of I. Okay, and this approach to parallel programming is called single program multiple data, where you have multiple threads all executing the same program, but each one of them operating on a different set of data. Okay. For those of you who have taken a computer architecture class, you may be familiar with SPMD, or single program multiple data. You may be familiar with that term. Okay, so now what we've done is we have implemented vector addition on the GPU. Okay, and it's nice and easy. We allocated data on the GPU. We copied the data to the GPU. We called a kernel and told it how many threads we want. And then each of these threads is going to come and it's going to execute this kernel function based on a different index. And then finally, we copy the result back from the GPU and we free the GPU memory. Okay?
Professor?
Yes.
Would it have been faster to write to X to save space Z?
I mean, yes, maybe you can do things like that. You know, you can write to X so that you don't have to, you have to save space. But maybe this is part of a bigger program where you need X for other things. Okay, so that just depends on the context. So don't worry about the context. In this case, we're just trying to demonstrate how to read from two arrays and write back to one array. Okay?
Okay, thank you.
Yeah, you're welcome. Okay, so then this is the kernel code that we just wrote, and the key thing here is that we have this expression blockdim.x times blocknx.x plus threadnx.x in order to identify the globals, the thread's global index. Now, there's one thing that you guys have, some of you have been mentioning, which is this n divided by 512. Some of you did not like that, and that's a good observation. So if you remember, over here, the way we got n threads is by having 512 threads per block and then doing n divided by 512. But if n is not a multiple of num threads per block, so if n is not a multiple of 512, what's going to happen? What does C do? What does division in C do? It takes the floor, right? C is going to take the floor. So if I do n over 512 and n is not a multiple of 512, right? So for example, if I have 1024 over 512, then my number of blocks is going to be 2. But if I have 1023 over 512, that will evaluate to 1 because division in C takes the floor. So I'm going to only have 1 block, and 1 block is only going to give me 512 threads, not 1023 threads. So what should I do in this case? If I want 1023 threads, what should I do?
We should round up.
Right, we should round up. So we should take the ceiling. So in other words, I want to take the ceiling, and what the ceiling will do is that it will launch extra threads, and then somehow in the code I'm going to have to eliminate these extra threads and ask them not to do it. Okay. So in other words, if my array here did not have 16 elements like in the original case, if it only had 14 elements, then in this case, I only need 14 threads, but I don't have a way to launch 14 threads because my thread block is 4. So I'm going to launch 4 blocks, which is going to give me 16 threads, but then I'm going to have some kind of check to make sure that these last 2 threads don't do any work. Okay, so let's go back to the code. So here, when I calculate the number of blocks, we said that I don't want to just do n over 512 because if n is not a multiple of 512, I'm going to get the floor and I want the ceiling. So instead, I want to do the ceiling, and the way to do the ceiling is there's many different ways you can do ceiling. Some people cast it to a float, do ceiling division, and then cast it back to an int. Some people just use some integer arithmetic. So one thing you can do is you can do n plus 512 minus 1 over 512. And this calculation over here effectively calculates a ceiling division. Okay, I'm not going to get into why. You can go on your own and verify that this arithmetic over here will do a ceiling division. By the way, I'm writing 512 over here, but it's actually good practice for me to actually use num threads per block. The reason is that if I come and change the number of threads per block, I only want to change it in one place. I don't have to go and change it in 3 different places. Okay, so by doing this now, I've taken the ceiling, so I launched the ceiling number of threads, and then I go back here to the code and to my GPU code. Now it could be the case that I have more threads than the array bound. So I want to make sure that these last threads don't access any memory, because then their access will be out of bounds. And the way I do that is by simply making sure that my thread index is smaller than the size of my array. So here, before doing z of I equals x of I plus y of I, I'm going to do if I is less than 10. Okay, and we call this a boundary condition, because we don't need these threads. The reason we have them is because of the way that CUDA forces us to organize our threads into blocks. Okay, clear?
Professor?
Yes.
Doesn't adding like the if condition add a lot of processing? Like there might be branches and so on. Wouldn't it have been easier to just do another separate block for the last chunk?
So you have a trade-off, right? If you have a trade-off between having this if statement that all the threads are going to execute versus having to launch. If you want to do a separate block for the last chunk, you're going to have to launch a whole new grid specifically for that one block. And launching a grid also has its own overhead. Okay, so there's a trade-off you have to make, and most likely the overhead of this if statement is going to be much less than the overhead of launching a whole new block. Okay.
Okay, thank you.
Yeah, you're welcome. Somebody's asking, does number of threads per block have to be a power of 2? It doesn't actually. It can be any number, but it turns out that it's actually a good idea for this value to be a multiple of 32, and we will talk about that later on in the course. Okay. All right. So this is the code that we just wrote. The next step, now that we have this code, is compiling the code. So somebody had previously asking about compiling. So now we'll see how we compile this code. So to compile this code is in a .cu file. So this file that I've been editing is called vecadd.cu. Okay. So this vecadd.cu that I just edited. Okay. Now what I want to do is I want to compile it. So to compile it, there's a compiler called the NVIDIA CUDA compiler, or NVCC. And what NVCC does is that you can use it to compile this CUDA code, and gives you a binary. So I can write NVCC, okay, and I give it vecadd.cuda, and I write -o to tell it what the output. It's similar to the interface of GCC. I'm going to -o, and I can call my program whatever I want. I'm just going to call it vecadd in this case. So I compile, and now I have this binary over here called vecadd that I can run. Okay. Now, what does NVCC do when I call this? Well, let's see what it does. What NVCC is going to do is it's going to split our code into 2 parts. It's going to split it into the C++ code, and that code is going to be given to the host C or C++ compiler, and the C or C++ compiler is going to use this C code to generate a host assembly file, and this host assembly file is going to run on the CPU. On the other hand, some of the code in my CUDA file is not C code. Some of it is CUDA code. So this kernel that I implemented that had underscores from global before it, and that was using this blockindex.x and threadindex.x keywords, this is CUDA code, and this is going to run on the GPU, not on the CPU. So the compiler is also going to separate that code out. So it's going to separate out the CUDA code that's meant to run on the GPU, and it's going to compile it down to something called PTX, which is a virtual ISA. Okay, and then there's a just-in-time compiler that will take this PTX and compile it down to the device assembly language, for example, SAS. Okay, and this happens when I run my program. Okay, and then finally, this device assembly code is going to be run on the GPU. And what will happen is when I have this call to the kernel, when my CPU code calls the kernel, what the CPU code is going to do is it's going to somehow go and call this device assembly code on the GPU to run on the GPU. But for us, we don't have to worry about any of this. The NVIDIA compiler does that automatically for us. It takes the code in one CUDA file, separates it into C code and CPU code and GPU code, compiles the CPU code to the CPU, compiles the GPU code to the GPU, and makes sure that the CPU code knows how to call the GPU. Okay? Clear? How does it know? Someone's asking, how does it know what code goes to the CPU and what code goes to the GPU? Well, it knows from these function declarations. And actually, that was the next slide. So we have keywords that differentiate where a function is intended to run. Okay. We saw the global keyword. The global keyword indicates that this is a kernel function that is called from the CPU and that or the host and that is executed on the GPU. Okay. We also have another type of function, which is a host function. And the host function, this is basically the regular C function. So if I don't write anything before my function, by default, this is a host function that runs on the CPU. And then there's a third kind of function, which is a device function, which runs on the, which is a function that runs on the GPU, called on the GPU and runs on the GPU. Okay, so here, if my CUDA code here is very long, if this is a very complicated operation, I actually don't need to write, put all this code in one function, right? I can create a device function that does it for me. Okay. And I'll show you an example in a bit. But one question is, why do I need the host keyword? Okay, why do I need the host keyword? If all my functions by default are host, then why would I even need a host keyword in CUDA? And the answer is that sometimes I might need to label something as host in order for me to be able to run it on both. I might need to label something as host if I want to label it as both host and device. So let me give you an example of what I mean here. So let's say here this add operation was a very complicated operation. Okay, and this add operation is an operation that I'm doing in both my CPU version and my GPU version. Okay, so rather than having to replicate this code on both the CPU and the GPU, what I can do is I can simply define a function. Okay, I'm going to call it divide. Well, let me do this. I'm going to define a function. I'm going to call it f. Okay, actually, it's going to return an int or a float. I'm going to define a function, float f, that takes two floats, a and b, okay, and adds them and returns their sum. Okay. Okay. So here, instead of doing x of I plus y of I, I can do f of x of I, y of I. Okay, so here, this function f is going to add x of I and y of I. And similarly, down here, I can call f of xi and yi. Now, I would like to be able to do this, right? Because if this operation is a very complicated operation, I don't want to have to copy the code inside of this loop was the same as the code inside of this kernel. So I don't want to have to write this code, copy and paste this code down here. Okay. So one thing I could do is I could factor this code out into a function. But the problem here is this function f is by default only compiled for the CPU. It's not going to be compiled for the GPU. So the CPU function is going to be able to call it, but this GPU function is not going to be able to call it because the code for f is not going to be on the GPU. So what we can do if we want the code for f to be on the GPU is write device. Okay. So now that I write device, now this function is going to be compiled for the GPU. But the problem is that now the function will only be compiled for the GPU and not for the CPU. If I want it to be compiled for both, then I will have to write this, host device. So when I write host device before F, now the compiler knows to generate two versions of F, one version to run on the CPU for the CPU function to call, and one version to run on the GPU for the GPU function to call. Okay? Is that clear? So really, this is useful for software engineering reasons, just so that we don't have to duplicate our code.
But Professor,
yes.
I mean, typically, if you're implementing this function on the GPU, it's because you don't want to execute it on the CPU, right? So I mean, I don't see where this would be useful.
Right, you're absolutely right. But you can imagine somebody, maybe some of our physics colleagues over here who are attending this course. Maybe they have this high performance code that they would like to run, and sometimes they have access to GPUs and sometimes they don't.
Oh, okay.
Right, so they might want to sometimes run their code on GPU, sometimes they want to run their code on the CPU. So rather than having to duplicate their code, they can simply use this approach to make sure they have as little code duplication as possible.
Thank you.
Okay. All right, so now that we have this, let me compile it again. Okay, and notice it compiles. If I didn't put host device, it would not have compiled. And now, and then this over here is the code that we just wrote. So now we have a complete CUDA program that is able to do vector addition on both CPU and GPU. And we also didn't have to duplicate this complicated code that does the addition. We were able to have a function that we can execute, a call from both the CPU and the GPU, and the compiler automatically generates two versions for it. Okay, so the question is, now that we have all this, how much faster does this execute? Okay, and to do that, I'm going to run this binary to see the performance improvement that I get. Okay, so I ran it. So the CPU time, remember I had some timers inside of my code. On the CPU, it took 0.22 seconds, and on the GPU, it took 0.12 seconds. Okay, so you'll notice that the GPU is faster. But some of you are probably disappointed right now. You're probably expecting to see something like 100 times faster, and all you see is now, less than 2 times faster. Well, don't be too disappointed. Somebody's asking what was n in this case. This is a very good question. So n, let me check actually, just to make sure. So n in this case was 2 to the power 25. So it was around 32 million elements. Okay. Okay, so you're probably asking, this is not that impressive. And one thing to keep in mind is that this timing includes a lot of things. This timing includes the time it takes to copy from the CPU to the GPU, the time it takes to do the allocation, the time it takes to do the copy, the time it takes to run the code, the time it takes to copy back, and the time it takes to do the deallocation. But normally, when you're running a program on the GPU, you don't copy data to the GPU and back for every function that you call. You normally put your data on the GPU, run a whole bunch of long-running operations, and you call multiple kernels, and then you copy the data back. Okay, so let's go and take a look at how much just the computation takes. Okay, so if I only wanted to call if I only want to see how long this kernel takes to execute, let me just time this. I'm gonna do timer, and I'm gonna do start time. By the way, CUDA has built-in support for timing things on the GPU that is more reliable. But for now, I don't want to worry too much about that, so as not to complicate the code. So I'm just using some CPU timers that I define. Okay, so here I'm going to do stop time, and then I'm going to print elapsed time, and this is going to be the GPU kernel time, and I'm going to color that green. Okay, and there's something I need to do over here to make sure that I time things correctly, and I'll explain to you why I'm doing this. I'm going to have to call CUDA device synchronize. I will tell you why. Basically, what this is doing is it's waiting for this kernel to finish executing before it stops the timer. And I will tell you. I will tell you why we need to do that. Okay, so now that I've done this, let me recompile. Okay, and now let me run. Okay, so the kernel time actually takes 0.003 seconds. So now when you compare the time for doing the vector addition only to the time for doing the vector addition only on the CPU, you'll notice that that it's much faster. So most of the time was actually spent doing the allocation and the copy. Okay, but in normal programs, you don't do allocation and copy for every single function. You do that once at the you copy to the GPU once at the beginning. You run your program, which is taking you hours on the CPU, so that it takes you minutes on the GPU, and then you copy the data back at the end. Okay. Quick note about kernel asynchronous kernel calls. So by default, when I call a kernel, it's asynchronous. So by default over here, when I call vec add kernel, what the CPU does, it will call this kernel. This kernel will go and start running on the GPU. The grid, we launch a grid. The grid starts running on the GPU, and then the CPU actually continues on executing. It doesn't wait for the GPU to finish. And what this does is that it allows you to run things in parallel between the CPU and the GPU. So the CPU can do some things while the GPU is doing other things. So the reason I put CUDA now, if we don't want the CPU to keep executing, if we want to wait for the GPU kernel to finish before we continue, then we have to call CUDA device synchronize. So the reason I called CUDA device synchronize over here is because I wanted to wait for the GPU kernel to finish before I stopped my timer. Okay, so this is why I had CUDA device synchronize over here. Okay, so you can use CUDA device synchronize to synchronize, to wait for the kernel to finish. Finally, error checking. CUDA has this error code, CUDA error T, which we saw, which is used to check for errors. And the way we check for errors is like this. So CUDA error T, and then we do if error does not equal CUDA success, then we can have some code for error handling. So here, if I wanted to check if my kernel had an error, what I could have done is I could have written CUDA error underscore T, error, I can call it anything I want, and then I can do something like if error does not equal CUDA success, and then over here I can do a whole bunch of things to handle this error, maybe check the reason why this error happened. One thing I could do is call a function CUDA get last error that gives me information about what was the last error that took. Okay. With that said, you just learned CUDA. Okay, so you just learned CUDA. Now you know how to take code that runs on the CPU and copy the data to the GPU, run it in parallel on the GPU, and then copy the result back. The rest of this course is about parallelization strategies and optimizations that we can apply in order for us to get good performance out of our code. Obviously, if you're taking a parallel programming course, you care about performance. So I hope that you stay in this course. But if you took this course only because you wanted to learn how to write a CUDA program, then you already know how to do that now at the end of this lecture. And in fact, after this lecture, we will release the first homework assignment where you will be asked to write a simple CUDA program similar to the one that we wrote today. Okay, for more information about what we talked about today, you can refer to chapter 2 of the textbook. And that is all for today, and I will see you next time.
Thank you, Professor.